Hey guys, welcome back. Calculus with polar coordinates. Let's start with a quick review. Remember rectangular coordinates. Rectangular coordinates are going to be x, comma, y. An equation will be y equals f of x. So an example of that would be something like y equals x squared plus 3x plus 5. Okay? Polar coordinates, on the other hand, is going to be r, comma, theta. And this is a circular set of coordinates. It works very well for things like circles, cardioids, rose curves, things that are very difficult to define in rectangular coordinates. And this is going to be r equals a function of theta. R equals a function of theta. An example of a polar curve would be r equals 3 cosine 2 theta. Okay, so that'd be an example of a polar curve. Now, what we would like to do is we'd like to make a couple of definitions. The first thing I'm going to start with is a reminder to convert from rectangular to polar and polar to rectangular. If you are given a rectangular coordinate, r will always be x squared plus y squared under the square root, and that's just Pythagorean's theorem. And theta will always be the inverse tangent or the arctangent of y over x. And so if you're given rectangular coordinates x and y, you can convert those into polar coordinates r and theta. And polar coordinates likewise, x will be r cosine theta and y will be r sine theta. And we'll use these four equations quite a bit. Given a polar coordinate r and theta, you can find x and y. Okay, so that's just a quick review of polar and rectangular coordinates. Now, real quick, folks, if you remember from parametric equations, let's talk about dy dx. Okay, if we are given a polar curve and we want to find dy dx, and we have something defined in theta, a function of theta, this would be equal to dy d theta over dx d theta. Okay, so dy d theta over dx d theta. Now, dy d theta would be d theta of, and I'm going to use the product rule, and what I'm going to do is I'm going to define this as y. Okay, so I'm going to find dy d theta of this, okay, which would be, instead of calling it r sine theta, I'm going to call this f of theta times sine of theta, and I'm going to call this f of theta times cosine of theta. Now, d theta of this, which would be dy d theta, is going to be the product rule. So it's going to be the derivative of f of theta times sine of theta, and dx d theta will be d theta of f of theta times cosine of theta. And if I use the product rule on both of these, I'm going to get f prime of theta times sine of theta. And then it's going to be, remember the product rule is a prime b plus ab prime. So it'll be f of theta times cosine of theta. And if I do the same thing on the bottom, a prime b plus ab prime, right? So the derivative of the first times the second plus the second times the derivative of the first, I'm going to get f prime of theta cosine of theta. Now, the second one is going to be f prime of theta times, and the derivative of cosine will be negative sine. So that'll be sine of theta, and the negative will come out here. And so we get something that looks like that. Okay? And so what that gives us is it gives us a rule that we can use in polar coordinates. And here's what it says. Given r equals f of theta, okay, some function of theta, dy dx will be f prime of theta sine of theta plus f of theta cosine of theta divided by f prime of theta cosine theta minus f of theta sine theta. Okay, so this is a rule we can use for derivatives in polar coordinates. Very, very, very important to keep in mind. So that's the first thing I want you to know. That's our derivative rule for polar coordinates. Probably a great idea to write that down somewhere. Going to come in real handy. Okay, so that's the first thing. Now, second thing I want to do is kind of draw you a picture. I want to draw you a picture. So remember, polar coordinates are an r theta proposition. So if I've got an xy axis here, okay, so here's xy axis, okay, and I've got some curve. I'm going to draw this curve in a different color. I've got some crazy curve. Who knows? Okay, I've got some crazy curve here. And this curve is r equals f of theta. Okay, r equals f of theta. Okay. Normally, when we think about working in calculus, we work with small sections, right? So we're going to talk about integration. And integration in polar coordinates, if you recall, integrating, we have an integration, a piece, you know, a dx, a slice, right? We think of volumes, we think of areas. You always have this slice, this integral piece, and the sum of all those pieces equals the integral. Well, in polar coordinates, your slice is going to be like this. It's going to be a sector. It's going to be a sector. Okay? So, if you look at this curve and you think of this slice is our d theta. Okay? This slice is our d theta. And I'll remind you from pre-calculus, the area of a sector is 1/2 r squared theta. Okay, 1/2 r squared theta. Okay, 1/2 r squared theta. Now that's from pre-calculus. Now if we put this in calculus notation, this will become 1/2. And remember, our function will be defined as r, which is f of theta. So this becomes f of theta squared, right? And our theta will actually be, instead of being the angle of the sector, this will be d theta. Okay, this will be d theta or delta theta, right? If you think of this as delta theta or d theta. Okay, it's 1/2 f of theta squared d theta. Okay, so what we do is this is the area of one slice, and the sum of the slices will equal the integral. Okay, the sum of the slices will equal the integral. So if I sum my slices, what I end up with, the sum of the slices is equal to the integral. So I end up, if I sum, and let me come in here and say we got some point A on the curve, and we got some point B on the curve. If I sum from point A to point B, 1/2 f of theta squared delta theta. If I sum those, I get 1/2 the integral from A to B, right? 1/2 the integral from A to B, f of theta squared d theta. Okay, so that is the area bounded by a polar curve. So the area bounded by a polar curve will be equal to 1/2 integral A to B f of theta squared d theta. Okay, f of theta squared d theta. So instead of f of x, it's f of theta. So you're going to square your function, integrate with respect to theta from a to b. Okay. Now I will warn you, you have got to be in radian mode to apply this. You have got to be in radian mode to apply this. Now, one more definition, and I'm gonna kind of skip. I'm at the bottom of my paper here, and I'm gonna skip just a little bit on this, and just kind of show you the gist of this. But if I come back to my drawing and I take this here as the outer diameter, okay, so this is R2, right? So that's R2, and then I come make some inner diameter R1, right? If we remember from earlier in the semester in Calculus 2, the radius 2 minus radius 1, or I would say big R minus little r, would give us the area of, remember, disk versus washer method. And so if I apply this definition, okay, and I say R2 minus R1, and I say R2 was f of theta, and I say R2 was g of theta, right? And I apply this to a polar curve with a hole or with an inner radius, okay, we could say that this area with an inner radius, if I can spell radius right, is equal to 1/2 integral from a to b, and it's going to be what? It's going to be f of theta minus g of theta, okay? And do remember, it is to square this term and square this term, not to square the quantity d theta, okay? So that is the area with an inner radius. And so those are the derivations of our formulas that we're going to use in this section in calculus. So how to find derivatives and how to find integrals. One last thing we need to do, we're going to revisit arc length. Now, arc length, if you recall earlier in this text, arc length was equal to the integral from a to b of the square root of 1 plus f of x squared dx, okay, which we derived this from the square root of delta x squared plus delta y squared, which really we just derived from the distance formula, but we use that as, you know, we use that on a curve. We use the distance formula on a curve. So what I want to do is I want to apply polar coordinates to this. So what I want to do, remember, x is equal to r cosine theta, or f of theta cosine theta, and y is equal to r sine theta, or f of theta sine theta. And if I think of delta x would be the derivative of this. It would be dx d theta, right? So delta x would be dx d theta, and delta y would be dy d theta. And we already have definitions for those. And so what I'm going to do is I'm going to say arc length is equal to the square root of dx d theta squared plus dy d theta squared. Okay, let's plug that in. And what we're going to do is we're going to plug in. This is going to be fun. We're going to plug in. It's going to be the integral from a to b, okay, of all of this. And it's going to be with respect to theta. Okay, it's going to be with respect to theta. Dx d theta, if you look back in our notes in this video, was going to be f prime of theta cosine theta minus f of theta sine theta. And that's going to be squared. And dy d theta was f prime of theta sine of theta plus f of theta cosine theta squared. We're going to square all of that. And of course, that's still going to be integrated from a to b. Still going to be integrated from a to b with respect to theta. Now, here's where it gets weird. Let me make sure I don't lose you in all of this. We're going to square that. We're going to square that, right? So it's going to be that good old binomial square. Here's what we get. We get that arc length is equal to the integral from a to b of, let me write all this out. Yes, it is going to be that long. Here goes. It is going to be f prime of theta squared cosine squared theta minus 2 f of theta f prime of theta cosine theta sine theta minus, it'll be plus, because when I square that minus, I get a plus, so it'll be plus f of theta squared sine squared theta. Sine squared theta. That is this first piece squared. Okay, so that is this guy here squared. Then it'll be plus, oh boy, so I'm going to put brackets around that just so that you know that's that first piece. Now we're going to square this second piece. Same kind of thing. What are we going to get? We're going to get f prime of theta squared sine squared theta. Then we'll get plus 2 f of theta, f prime of theta, times cosine theta sine theta. Ooh, I'm going to run out of room here. Then plus f squared, f of theta squared, f of theta squared, cosine squared. Let me get my right trig here, theta. And all of that will be integrated with respect to theta. Get my radical all the way out here. Now, something magical happens. This piece here, let me get a different color. This piece here and this piece here are equal but opposite. They will cancel. Yay! That helps a lot. I get f prime squared cosine squared, f of theta squared cosine squared, and I get f of theta squared sine squared and f prime squared sine squared. So I'm going to combine my like terms. I'm going to combine all my like terms, and when I combine those like terms, I end up with arc length is equal to the integral from a to b of, and I get f prime squared, f prime of theta squared plus f of theta squared d theta. Now I know you're looking at this and saying, wait, what happened? Pay attention. F prime squared cosine squared, f prime squared sine squared. Okay, and it's going to be this plus this. If I factor out the f prime, I get a cosine squared plus a sine squared. Well, cosine squared plus sine squared equals 1. That only leaves me f prime of theta squared. Okay, now let me get a different color. Same thing. I'm going to take f of theta squared sine squared and f of theta squared cosine squared. And if I factor out the f of theta squared, I get a sine squared plus a cosine squared, also a 1. And I'm left with f prime of theta squared. Okay, so that is arc length in polar coordinates. Arc length in polar coordinates. Okay, so these are our formulas we can use in calculus for polar coordinates. So jot these down. They're going to come in really handy for all of the questions in polar coordinates for the rest of Calc 2 as well as all of Calculus 3 anytime we're working in polar coordinates. If you have any questions, let me know, and I hope this helps.